So, we will continue our discussion on slip, that is departure of Euler's theory. We have seen that the actual head developed by the pump is always less than that of the ideal head, that is the head predicted by Euler's theory. We have tried to quantify that what would be the possible reasons for which this is happening. In fact, we have seen that slip is one important factor by which we always get reduced head, which is not the head developed by the pump, following the Euler's equation. So, we have seen that if we calculate head developed by a pump using Euler's theory, then of course we will get ideal head, and it is not the case that always we will get the actual ideal head, because losses, separation losses, frictional losses, and also the presence of non-uniform velocities give rise to a deviation, this deviation. We have quantified, rather we have predicted the amount of slip, because our discussion today, our discussion was on basically slip velocity, and we have seen that mainly there are two reasons. One is the non-uniformity of the velocities because of the existence of the blades, and of course the formation of boundary layer. There are separation losses, frictional losses, and losses due to wave formation. So, we have written that due to non-uniform velocity distribution there is a circulation around the blade, and because of these circulations the mean velocity, the mean direction of flow leaving the impeller changes from beta 2 to beta 2 prime, where beta 2 and beta 2 prime the blade angle at the outlet, and due to the change in mean direction of flow at the impeller outlet, there is a reduction of very important or all important velocity component, that is Soal component or wall component, which is called slip. So, a change in Soal velocity at the outlet, a change in wall velocity at the outlet, c theta 2 at the outlet, the deviation or a change because of the change of mean direction of the flow, that is essentially because of the non-uniform velocities at the outlet of the impeller. There is a slip, and that slip is responsible for the reduction of head, which is predicted by Euler's theory. So, we have understood that several reasons like frictional losses, and also the several losses due to recirculation, separation, and this is happening. So, the earliest we have seen that there are many formulas which have used to predict this amount of slip, but the Stordala who earliest due to Stordala, who stipulates that existence of relative AD, which occurs between the adjacent blades. And we have seen, following Stordala, we have tried to quantify the amount of slip, and Stordala assumed that whenever a frictionless flow is flowing through the passage of the impeller, that means it must leave the impeller without rotation. If a frictionless flow passes through the impeller without rotation, that means it must leave impeller without rotation. And if we assume that the impeller is rotating at an angular velocity omega, that means relative to the impeller, fluid must have a rotation in the negative omega, which is the relative AD. And Stordala assumed that if a velocity, we would like to calculate the slip velocity, that means this is happening at the impeller outlet. So diminished, rather reduction of Soal component or wall component of velocity at the outlet is responsible for this deviation, deviation of the actual energy transfer. Then Stordala assumed that if a circle of radius E can be inscribed at the outlet of the impeller, then from the geometry and from very simple trigonometric calculation, we have calculated that the diameter of the circle can be expressed in terms of the blade angle at the outlet, radius of the impeller at the outlet, and the number of blades. And the slip velocity, which is according to Stordala's model, is the omega, that is the angular velocity to the angular velocity of the impeller the slip velocity can be calculated following Stordala's model, that is the product of angular velocity omega and the radius of the circle, which is inscribed at the outlet of the impeller. So, and following that, we have arrived at this expression of slip velocity at the outlet of the impeller. If we draw the velocity triangles at the outlet again, suppose we are having an impeller, pump impeller. So, if we have a impeller and if we draw, suppose this impeller is rotating at angular velocity omega, and if we just draw a velocity single blade 1 2, and if I draw the velocity triangles at the outlet, so we have seen that there is a change in mean direction of the flow at the outlet which changes beta 2 with a change in beta 2 from beta 2 prime. That is what we have seen, that because of the non uniformity of the velocity distribution which is responsible for the mean direction of flow leaving the impeller to be changed from beta 2 beta 2 prime. So, if I draw the velocity triangle at the outlet, if this is the absolute velocity at the this is the relative velocity at the outlet, but it changes because of this non uniformity, and this is W 2 prime, this is W 2. So, this was beta 2 and this is beta 2 prime. So, the angle changes from beta 2 to beta 2 prime because of this non uniformity of the velocity distribution, which is essentially because of the circulation, and these changes of blade angle from beta 2 to beta 2 is responsible for the change in it reduces the all important Swirl component velocity at the outlet. So, if we draw, this is the absolute velocity at the outlet C 2 and this is U 2. So, the absolute velocity changes from C 2 to C 2 prime, and this is known as slip velocity V s. So, this was C theta 2 and this is C theta 2, this is C theta 2 and this is C theta 2 prime. So, we have seen that the main reason is that because of non-uniform velocities, of course, solid surfaces are there, blade and existence of blade, formation of boundary layer, the direction of mean direction of flow leaving the impeller changes, which also reduces the wall component of velocity by changing the absolute velocity at the outlet. So, the absolute velocity of the outlet changes from C 2 to C 2 prime, as a result of which it reduces the wall component of velocity at the outlet, that is from C theta 2 to C theta 2 prime. So, now this V s is essentially C theta 2 minus C theta 2 prime. So, a change in Swirl component of velocity at the outlet because of this change in the mean direction of flow at the outlet of the impeller, we got this slip velocity. So, now this is the quantification of slip velocity, and we have calculated that slip velocity can be expressed in terms of pi into u 2 sin beta 2 divided by z. That is what we have written in the pi u 2 sin beta 2 by z, the same, that is the expression of slip velocity at the for the pump operation. So, the slip velocity, because of the velocity slip, we do not get the actual ideal head. So, we always get the actual head, which is always less than the ideal head. Apart from this, there are I will now try to explain slip from different perspective. Okay, Stodolph first stipulates the existence of relative eddy at the pump in the which occurs between the blade passage, and because of what we always get the diminished strength of swirl velocity at the outlet, as a result of which we always get a reduction in the head. Now, for a radial flow pump, there is another argument from which we can explain that the reduction of slip velocity at the outlet. So, if I now draw an impeller, if a blade, if I draw again an impeller of a radial flow pump, and suppose this impeller is rotating at an angular velocity omega. So, impeller of a radial flow pump, this impeller is rotating at an angular velocity omega. So, this is impeller of a radial flow pump and impeller is rotating at an angular velocity omega. And so, whenever this impeller is rotating at an angular velocity omega, we have seen that these liquids are, this is on the liquids are moving like this, liquids are flowing out like this. So, liquids are moving like this. And this is in-housed in a casing. So, and there is a flow passage, and while it is moving through the casing and it is ultimately going out. Now, there is an argument, then when it is rotating, suppose if I take this blade, and if I take out this blade and if I draw the enlarged view, so there are two surfaces 1 1 and 2 2. So, 2 2 is the convex or upper surface, 1 1 is the lower surface, concave or lower surface. So, now when this pump is rotating, right. So, when pump is rotating, so I am writing when pump is rotating in clockwise direction, then a vector will be in the direction perpendicular to this board. On the other hand, water or fluid, a vector will be acting, water or fluid is flowing in the upward direction. So, if I take this particular two blades, one is AB, another is CD. So, this is 1 1 surface, lower surface, 2 2 surface is the upper surface, 1 1 is the lower surface, and this is AB and this is CD, two adjacent blade we have considered. So, whenever this impeller is rotating, of course, a vector will be acting in the direction perpendicular to this plane of this board, and on the other hand water is flowing out. So, water is flowing out. So, this is water flowing out. So, a force will be in this direction, that is perpendicular to the plane of the board, and water is flowing out in the upward direction. So, this is the water is flowing out in the upward direction as shown in figure, let us say 2. So, this is figure 2. So, a force is acting in the direction perpendicular to the plane of the board, on the other hand water is flowing out in the upward direction. So, there will be a result because of this, right, because of this, as per Fleming's rule, a resultant force or vector will be acting so this is water flowing out in the upward direction and a resultant will be acting in this direction as let us say this is resultant force R. Resultant force will be acting as shown in figure 2 by R, right. So, we have discussed in the previous lecture that the non-uniform velocity distribution, and we have seen that velocity at the upper side will be always higher lesser because of the higher pressure, because pressure will be higher. We have seen that blades do work on the fluid by exerting an impelling force on it, and because of which pressure at the upper side of the blade will be always higher than the lower side, and since the pressure at the upper side of the blade is higher than the lower side, there will be a mismatch of the velocities. Rather, velocities will be higher at the lower side, velocity will be lesser at the upper side, and because of this change in velocity there will be a circulation that is represented by gamma b. And whenever velocity is, since pressure is higher, so force will be higher on the upper side. Now, we have seen that because of the circulation, which is stemming from the non-uniformity in the velocity distribution, there is a reduction in all important swirl velocity due to a change in direction of mean flow at the outlet of the impeller, and ultimately we have calculated that because of this change in swirl component of velocity, there is a change in head developed by the pump. Rather, to be precise, the absolute velocity at the outlet of the impeller is changing from C2 to C2 prime, and as a result of which we are getting a lesser amount of swirl velocity at the outlet, so it reduces the head. Now, we are trying to explain, rather we are trying to understand this from a very from a different perspective, and it is from our this is not that Stradula's model. Many theories have been formulated to predict the, rather to quantify the slip, but this is what we are discussing to for our own understanding, that how we can understand the reduction of absolute swirl component velocity at the outlet of the impeller. So, and in order to do so, what we have done, that we have considered a radial flow pump, the impeller of a radial flow pump which is rotating in a clockwise direction at an angular velocity omega. We have drawn figure 1 and figure 2. Figure 1 which show the impeller of a radial flow pump, and figure 2 I have taken two adjacent blades A, B and C, D. We have seen that 2 are the upper surface of the blade and 1 are the lower surface of the blade. So, if I take two adjacent blades, then of course water is flowing out in the upward direction because of this rotation of the impeller. Now, whenever impeller is rotating, so a force or a vector will be acting in the direction perpendicular to the plane of the paper, and water is flowing out in the upward direction. So, there will be a resultant vector as per Fleming's rule, there will be a resultant vector. So, because of this there will be a resultant vector which will be acting in the direction as shown in figure 2, that is R. And because of this resultant force, pressure at 2 dash and 1 dash, 2 dash surface will be higher than the 1 dash surface. So, the resultant force is acting on the upper surface of the blade. So, pressure will be higher on that surface, that is pressure at 2 surface will be always higher than the 1 surface, that is pressure at the convex surface will be higher at the convex surface. So, pressure at the convex surface will be higher and pressure at the concave surface will be lower. If that is the case, because of this change in pressure, pressure at the convex surface is higher and pressure at the concave surface is lower. In the last case we have discussed that of course pressure difference, we have seen that. So since it is rotating, of course it is blades are working on the fluid by exerting an force, so of course pressure will be higher. From here the same thing, but we are trying to discuss from different perspective. So we have seen that this is not wrong, but what we have seen that whenever impeller is rotating, so our vector will be acting in the direction perpendicular to the paper, and since water is emerging out, so there, and that is in upward direction, so as per Fleming's rule there will be a resultant force which will be acting on the upper surface, that is denoted by R. So the force which is acting on the upper surface, naturally pressure at the upper surface will be higher, and at the lower surface pressure will be less. Now since the pressure at the upper surface is higher and then the lower surface, so it will try to, if I draw again one velocity triangles. So if I draw the impeller, and if I draw the velocity triangles at the this is C2, this is W2. Now this is W2 prime, this is W2, this is beta 2, this is beta 2 prime, this is U2. Now the new absolute velocity will be C2 prime, this is alpha 2, this is alpha 2 prime, so this is C theta 2 prime, and this is slip velocity Vs. So pressure at the upper surface is always higher and pressure is at the lower surface is always lesser. I am denoting by positive and plus and minus sign. So now what we can say, that is pressure at the convex side is higher and the pressure at the concave side is lower, and because of this the velocity due to difference in pressure will be from. Because of this, if I now draw the two adjacent blades again, so here pressure is higher, here pressure is less. So pressure is higher, velocity is less, here pressure is, so this surface pressure is higher, velocity is less, this surface pressure is less, velocity high. So there will be a velocity direction like this. So this is the velocity direction due to difference in pressure, and due to this flow is not due to this velocity distribution, because pressure at the convex side is higher and pressure at the concave side is lower. So velocity will be just reverse. So we will have a velocity distribution like this, and due to this flow is not axisymmetric. Due to this flow is not axisymmetric. So suppose this is the direction of water leaving the impeller, and so this is the direction of water leaving the impeller. So the resultant force is acting in this direction. So this is R, resultant force. R is the resultant force. Acting on the upper surface of the blade. So, the resultant force acting on the upper surface of the blade that we have seen, that is on the because of this two components of forces. I mean, one is because of the rotation of the impeller, which is in the direction perpendicular to the plane of this board, and another is the water leaving or water emerging out of the impeller in the upward direction. Because of this, Stadler assumed that the existence of relative eddy when he suggested that if a frictionless flow is flowing through the impeller without rotation, rather then it must leave the impeller without rotation, and if we assume that the impeller is rotating at an angular velocity omega, that means relative to the impeller fluid must have a rotation which is negative omega, and he predicted the slip velocity will be angular velocity times the E, if E is the circle can be inscribed at the outlet of the impeller. Now, in this case we can say that due to this resultant force, the absolute velocity and relative velocity. So, here the resultant force is acting on the upper surface of the blade. That means, if I now think that maybe the impeller is rotating at an angular velocity omega, but because of this resultant force the blade will feel a retardation. I mean, as if some force is trying to retard the movement of the blade, and as a result of which the absolute velocity and relative velocity are moving, rather I can say that absolute velocity and relative velocity are moving to, let us say this is if this is A and this is A prime and this is B prime, are moving to A prime and B prime respectively. Whose earlier position was A and B. So, we have seen that of course, higher pressure is responsible. We have seen that higher pressure, because of the higher pressure there is a circulation around the blade, and according to Stadler, who first predicted the slip velocity, which is angular velocity times the radius of the circle which may be inscribed at the outlet of the impeller, and we have understood that the non-uniform velocity distribution changes the mean direction of flow leaving the impeller, and because of this change in mean direction of the flow, the all important velocity component, that is swirl component of velocity, reduces. Here we have tried to understand the same phenomenon from a different perspective, but the mechanism is remaining almost same. So, the resultant force whenever it is acting on the upper surface of the blade, so as if it is trying to retard the movement, as if the blade is feeling some retardation effect because of this resultant force. Not only it feeling the retardation, because of this retardation, I mean because of the resultant force, the relative velocity and the absolute velocity, and relative velocity are moving to a new place, A prime and B prime, whose earlier positions was A and B. That is the absolute velocity C2 will become C2 prime, and relative velocity W2 will become W2 prime, right. So, here we have understood that the resultant force is trying to provide a retardation effect of the blade, as a result of which the absolute velocity and relative velocity are now changing to a new relative velocity and new absolute velocity C2 prime and W2 prime. And since we have identified that the slip velocity can be expressed Vs is equal to pi u2 sin beta 2 by z following Stodola's model, right, that is z is the number of blades. Now this sin beta 2 I can write in a bit different form, that it can be, since I have written in terms of blade angle at the outlet, I also can write in terms of flow angle at the outlet. Now we can define one factor which is known as slip factor. So if I go to next slide, so we have seen that whatever it is, the main mechanism of having this undesirable phenomenon slip, this is not desirable because it always reduces the head of the palm, is only because of non-uniform velocity distribution. We have tried to quantify it using a Stodola's model, which predicted the existence of relative AD between two adjacent blades, but again also we have tried to understand it from a different perspective, although the mechanism is remaining same, that whenever an impeller is rotating and water is emerging out in the upward direction, so it is rotating means we will have a force in the direction perpendicular to the plane of the board, and whenever water is emerging out from the impeller, then we are having an upward force in the upward direction. So as per Fleming's rules, there will be a resultant force or vector which is acting on the upper surface of the blade, and it is providing higher pressure at the upper surface of the blade, and this resultant because of this resultant force, as if the blade is feeling a retardation effect, so that the absolute velocity and relative velocity are now taking their different position, and since the absolute velocity is taking a different position, the swirl component, which is very important, will be a new swirl velocity c theta 2 prime. So we have seen that the swirl component of velocity was c theta 2 earlier, now it is changing to c theta 2 prime, and the ratio of these two component is known as slip factor sigma. So this is known as slip factor. Right. So this slip factor is defined as the ratio of tangential velocity, the tangential component of absolute velocity when the pump is rotating to the tangential component of absolute velocity in absence of palm rotation. That is, sigma is c theta 2 minus Vs divided by c theta 2, or 1 minus Vs by c theta 2, because if I draw the velocity triangles again, this is c theta c2, so this is c2 prime, this is W2, this is W2 prime, so this is Vs, this is c theta 2 and this is c theta 2 prime. So c theta 2 prime is equal to c theta 2 minus Vs. So sigma is equal to 1 minus Vs by c theta 2 is the slip factor. So sometimes we need to know what is the slip factor, or of course only for doing some numerical problem. So from here we can understand that the amount of slip velocity divided by the actual Schwann component velocity is very important, which gives an idea about the slip factor. So, we have understood the slip and why it is originating while pump is rotating. We have tried to explain it from two different perspectives, I mean from two different angles rather. Using Stodola's model, we have quantified the amount of slip, and also from we have understood the existence of slip while pump is rotating, that is mainly because of the non-uniform of the velocities, only presence of blades, and also the development of the boundary layer. Okay. So, we will work out one example on this, and probably that is only because of the slip. Very important is that we need to solve a numerical problem to calculate, because the head developed by the pump will be always less than the head predicted by the Euler equations. I would like to solve one numerical problem on this aspect, that is slip. So, I am writing the problem. 8 bladed radial flow pump has an impeller exit diameter of 20 centimeter. The width of the flow passage at impeller outlet being 1.5 centimeter. The backward curved vanes make an angle of 60 degree with axial direction. With axial direction, very important is the outlet flow direction, the outlet flow direction follows the blade angle closely in absence of rotation. I am underlining this sentence. This is very important. This sentence gives us a clue that the outlet flow direction follows the blade angle closely in absence of rotation. That means, whenever pump is rotating, the flow direction may not follow the blade angle. So, whatever we have discussed today, that because of this circulation, because of the non-uniformity of the velocity distribution around the blades, there is a change in mean direction of flow from beta 2 to beta 2 prime, which is responsible for the reduction in all important Schwann component velocity c theta 2, and which is called as slip. So, this sentence is giving us a clue that the outlet flow direction follows the blade angle closely in absence of rotation, but whenever there is a rotation, the flow direction may not follow the blade angle. So, there might be a slip. So, rotation, the pump runs at 2880 RPM, so that the head so that the head developed by the pump is related to the flow rate cube, which is given by meter cube per second, by H is equal to 74.4 minus 565.1 cube. Neglect blockage effects and all losses. Sketch the above relation is very important, because we have discussed so far the H cube curve of pump, and we have seen that the actual H cube curve is not the ideal one, because to take the effect of recirculation losses in the suction side and also the separation losses in the delivery side, it takes a new shape. So, sketch the above relation and briefly explain what you would expect the actual head flow, that is H cube, characteristics to look like. So, this is the problem we need to solve. This is a problem only on the slip. I would like to discuss this problem because we have we need to understand if really the slip is there, then what would be the actual head, and we have understood the mechanism of slip in a pump operation, and because of this slip there is a deviation of energy transfer that is predicted by Euler's equation and the real case. So, this is the problem where clue is given. The problem is not directly telling you that you need to consider slip while you are solving the problem, but there is a clue which is given that the outlet flow direction follows the blade angle closely in absence of rotation. That means, when rotation is there, the outlet flow angle will deviate from the blade angle, that is, it will change from beta 2 to beta 2 prime, and which is responsible for the change in rather for the reduction in the reduction of important component of velocity, swirl velocity, which is responsible for the development of the head. So, we will solve this problem in the next class, and we will continue our discussion on the slip in the next class. Okay, thank you.